Malus's law. Malus's law is used to predict the change in intensity of light when a polarized beam of light goes through a polarizer that they're not at 90 degrees, they're not directly lined up, but they're at some other angle. The intensity of light is proportional to the amplitude of the wave squared. So recall that we know that light is an electromagnetic wave, so we focus on the electric field. So it's going up and down. The amplitude is the maximum or minimum value of that electric field. The intensity depends on the amplitude squared. So if we can figure out what happens to the amplitude and then we can square it, then we can figure out how the intensity of the light is going to change as it goes through that polarizer. Just recall again, if we have a polarizer and we send light that's parallel to the polarizer through, it'll all get through. And if we have light that's polarized and we send it through a polarizer that's exactly 90 degrees to it, none of it will get through. So we need a relationship that will support that. Probably the easiest way to do this is to consider the polarizer to be straight up and down, and then let's imagine we're putting in light on some arbitrary angle like that. And let's just focus on half of the light, so we're not going to draw it up and down like that, just half of it. So if I overlay that on this, then I can consider this to be theta, or the angle between the polarizer and the light. So what's going to happen here is we can consider this this beam of light to be comprised of two components. A component that's parallel to the polarizer and a component that's perpendicular to the polarizer. What's going to happen as this light goes through is this component will get through and this component will not. So if I have original amplitude A here, and this is theta, the angle between my polarizer and my light, then the resulting amplitude that will get through is this component, A cos theta. So with that in mind, if I know that A cos theta gets through, my new light in comparison to my old light is A 0 cos theta. And if I know that's what happens to the amplitude and I know the intensity squared, then I can say that my intensity is equal to my old intensity times the cosine of theta, but this time squared. And that is how we can determine how much light or what intensity of light will get through a polarizer when they're not, again, perfectly lined up or completely opposite, but at some interesting angle. Using this, we can relate our change in amplitude to a change in intensity. So for example, this means that if I have a 1 watt light with an electric field that is directed 30 degrees to a polarizer, so if my polarizer is straight up and down, my light polarization is at 30 degrees to that, I can predict the intensity of the light that will go in. So I have light that will come out. I have 1 watt going in. How much will come out? I equals I naught cos squared theta. Cos because it's the component that's in line with it, and squared because it's related to the amplitude squared, not the amplitude directly. So I get 1 watt times cos squared of 30 degrees. And that works out to be, just grab a calculator here, cos 30 squared is 0.75 watts in this case, because that's what I did. Or alternatively, we get, if we know how much of our light came out, we can predict what the angle between the electric field and the polarizer must have been. So here, let's say I get 50% of my light out, so my new intensity is equal to 50% of my old intensity. So, and that's going to be equal to I naught cos squared theta. I's can't be 0, so I can happily get rid of them. Square root. And inverse I get 45 degrees. So that's it. That's how you can get to Malus's law and how you can use it.